Don't photos seem magical to you too? You trap light on a piece of paper and fix it there forever. But is that thing you fixed made of a single moment? Or are we looking at a frame where pieces from different times merge? Modern physics tells us something strange, and just as shocking, even hard to believe. For example, in this frame, the light reflecting from my daughter Nora's eyes and the light from the wall right behind her didn't start out at the same time. They reached the camera sensor at the same time, but one is older than the other by a billionth of a second. So we see a single frame. However, inside that frame, there are tiny time slices layered on top of each other. And here's the even stranger part. We don't feel it that way. The photo still feels like a single moment to us because light is so fast that even a few meters of difference in a room stays at the level of nanoseconds. But if the object we were looking at moved at a speed close to the speed of light, for example, if we could photograph a rocket at such a speed, then even those tiny delays would become significant. Because in that very short time it takes for light from the back of the object to reach the camera, the front would have moved to another position. So here's a question for you. If we could observe a car traveling at near the speed of light, how would we see it? Would the image change or would it stay the same? Our intuition tells us it wouldn't change. But if we could measure it with a magic ruler at that moment, we'd see it shorten in the direction of motion. Yes, the object really does shorten, but we don't see it that way. Instead, we see it as if it's rotated. Well, shouldn't one of them be wrong? But both are real. By the way, before preparing the video, I did a poll about this question. Naturally, most people chose the option, it flattens like a pancake, because the same thing comes to all of our minds. Since an object shortens in the direction of motion as it nears light speed, it should look squashed in a photo. In other words, it should appear to be flattened. To be honest, if I hadn't done deep research for this video, I would have thought the exact same thing at first. But the correct answer is this: the object would appear to be rotated. I'll explain why that is in just a moment. In fact, an experiment was even done that made this effect visible in a lab. I'll talk about that too. But first, let's get the basics straight. What exactly do we mean by measuring? It's actually determining the position of both ends of an object at once and calculating the distance. Seeing, however, means collecting information that light brings to us at different times and merging it into one image. What did special relativity, which Einstein proposed in 1905, tell us? As something approaches the speed of light, time and length don't remain the same. For an outside observer, time slows down, and objects contract and shorten in the direction of motion. In physics, this is called Lorentz contraction. The name comes from Lorentz, the physicist who first formulated this. This was such a disturbing idea that in 1931, a book called 100 Authors Against Einstein was published. Some critics argued that Einstein's theory was not a physical reality. They suggested that it was some kind of optical illusion. Because until then, in Newtonian physics, which ruled for millennia, a 1 meter object was still 1 meter, no matter where it went or how fast it moved. So they said objects don't actually shorten. We just think they do, they claimed. Others claimed that even if the theory were true, it wouldn't be visible to the naked eye. So the scientific world circled the same question for years. Does the object really contract and shorten, or does it just seem that way to us? There were strong theoretical answers, but testing this directly wasn't easy, folks. Because we can't just take an object and accelerate it to near the speed of light. And why's that? As you approach light speed, the energy required grows so much that doing this on a macro scale is nearly impossible today. That's why we're turning our attention elsewhere, to subatomic particles. Since their mass is incredibly small, we can accelerate them to near light speeds. So what do we use to do this? With this device, a particle accelerator. For example, in November 2010 at CERN, researchers accelerated lead ions in opposite directions to near light speed and collided them head-on. Thousands of new particles burst forth from the extreme energy density created in these collisions. Giant detectors measured the tracks of these particles to reconstruct exactly what happened in that moment. So they didn't just take a picture like a camera would. It collected the signals left behind by the particles. And what do you think the result was? The experimental data only made sense if these particles were contracting and shortening. In other words, it's impossible to understand how the collision occurred without assuming the nucleus contracted in the direction of motion. Of course, this doesn't show the contraction on its own like a photograph, but it shows that this part of relativity is consistent with experimental evidence. But even so, if we could look at that atomic nucleus passing by us at that speed, we wouldn't see it as a shrunken disk. Actually, Einstein's critics were wrong not once, but twice. First, they thought the contraction wasn't real. Second, they thought that if it were real, we'd also see it as contracted with our own eyes. However, the situation was exactly the opposite. The contraction is real, but that's not what's seen. So then, how would such an object appear to our eyes? We can't make out an atomic nucleus with our eyes, of course. So let's think about the same effect using a more understandable object, like a cube, for example. Look, just like this. As the object passes by us, we would see it as if it had rotated. In physics, this is called the Penrose-Terrell effect. In other words, when we measure the object while it's moving in a straight line, it turns out shorter in the direction of motion. But in the image, it doesn't look shortened. It looks as if it's slightly rotated. In 1959, physicists James Terrell and Roger Penrose reached the following conclusion. When an object travels near the speed of light, the light coming from its backside travels a longer distance to reach the camera. But the object is so fast that while that light is on its way, the object has already changed position. The camera combines light emitted from different points of the object at different moments into the same frame. Because of this, some surfaces that we normally shouldn't see from that angle also get mixed into the image. The resulting image shows us that the object hasn't shortened or contracted, but rather rotated. So the shortening in measurement is real, but what we see in the photo is something completely different. By the way, Penrose and Terrell weren't the first ones to tinker with this strange idea. In 1924, Austrian physicist Anton Lampa asked the question, if we saw a rod traveling near the speed of light, what would it look like? But this question was later shelved. James Terrell and Roger Penrose took that same idea off the shelf 35 years later. They sat down and calculated the geometry of what we call a photograph. They considered the rays reaching the camera at the same time, one by one. And the math said this, the contraction in measurement was real. But in the photo, the object was supposed to look as if it had rotated. Now look at this twist of history. The Penrose-Terrell effect, that is, this visual rotation phenomenon, became mathematically clear in 1959, about half a century after Einstein's theory of special relativity. Making this visible to the eye took almost another half century. Austrian scientists have managed to visualize the Penrose-Terrell effect in the lab for the first time, which we've known in theory for about 66 years but couldn't see directly. An image like this emerged. Look, do you see those strange bright lines in the middle? This, of course, isn't an image observed directly in a single frame. It was created by combining the data collected in the experiment on a computer. By the way, this news was reported on news sites with the headline, "The speed of light has been photographed," but that's a bit of an exaggerated statement. Because we're not talking about the speed of light, but the image of an object traveling near the speed of light. So why did it take so? As we said, accelerating an atomic nucleus is easy, but bringing a macro-scale object to a speed near the speed of light isn't that simple. In fact, even today's technology falls short for this. But on the other hand, measurement technology has advanced a lot. We can open and close the camera in very short time windows. This makes it possible to divide light into time slices and mimic this effect in the lab. A team from the University of Vienna did exactly that. They said, since we can't get an object close to the speed of light, let's control the light's arrival time instead of accelerating it. Sometimes the greatest discoveries aren't made with machines, but with the most cleverly thought out methods. They set up a rig like this. They placed a small cube on a table and set up an incredibly sensitive camera in front of it. But don't think of this camera as an ordinary one. It doesn't capture an image with a single exposure. It can capture light in picosecond time windows. The researchers moved the cube in very small increments. At each new position, they recorded the arrival time of the photons reflecting from that point. They repeated this process thousands of times. This allowed them to watch the movement of light as if it were in extreme slow motion, almost as if it were slowed down to the speed of a human walk. In the end, they had a massive pile of data containing the timing information of the light from every position of the cube. Then they combined these pieces on a computer to create a kind of virtual photograph. So what was the result? A rotating cube. So if this cube were actually traveling near the speed of light, this is how it would appear to our eyes. In other words, the image the computer created from this data was almost exactly what the theory predicted about 60 years ago. The photo didn't show us a contraction, but a visual sense of rotation. Of course, we're not talking about a real photograph here. This is an experimental simulation done in a laboratory setting. You can see those visuals when you examine the article on the subject. I've left the link in the description section for those who are curious. But it's not just limited to relativity. We see smaller versions of this in everyday life too. For example, a spinning propeller sometimes looks distorted in a photo. Or LED lights seem to be on constantly to us, but a camera sometimes captures them as if they're flickering. There's a similar logic with telescopes. The images produced by telescopes like the James Webb aren't just a single photo frame, they're processed and combined data hidden in the sensor. For instance, think of that famous deep field image from the James Webb. In this photo, we see the main galaxy cluster in the center as it was about 4.6 billion years ago. But this frame isn't a single shot. It's a combination of images gathered at different wavelengths. A single image featuring thousands of galaxies was created from a total of 12.5 hours of data. In this process, sensor data was processed, noise was filtered out, and information from different filters was overlaid. Let me give you a more striking example. Do you remember that famous shot shared in 2019? You know when we saw a photo of a black hole for the first time? That's how it was reflected in the news. If you remember, headlines were made saying the first ever photo of a black hole was taken. But this image isn't made up of a photo taken by a single telescope. Signals collected simultaneously by many telescopes around the world were brought together. Those signals were analyzed over the years. Then an image was created from that fragmented data using computers. So it's not like I just took a telescope and snapped a photo of a black hole. Actually, what's done in telescopes, detectors, and the experiment I mentioned in this video is the same. We're piecing together the fragments that light brings to us. It's the same in the darkest, most unreachable parts of the universe and in the photos we carry in our pockets. It's impossible to capture the moment exactly as it is. And when I look at this photo in my hand, I no longer see just a single moment. I see a delayed letter that the universe has sent to me. Light crosses distances and shatters time to bring my loved ones to me, and then reunites them in a single frame. That's why nothing is as it seems. So then, are we seeing the truth? Or just the version of the truth that has reached us?